It's a great pleasure. This is the last lecture of this series, Frontiers, so I'm really excited because this is an area that I'm extremely passionate about. I've been in the business of space since the beginning of my career, so I'm going to kind of interweave the formal part with some things about what I was doing at different times when space was making these great leaps forward. I also have to claim that when I gave the title of this talk to the Gresham College, little did I know, although I was subsequently told, that the BBC was going to bring out a big series called Earth from Space. So if you don't mind, I'm going to use some of the material because I think not only is it awe-inspiring, but it tells the message in such a brilliant way, much better than I could ever tell you. So I would encourage those of you who haven't watched the series to take a moment and just sit back and watch it and relax. But I'm going to use just a few points from it. So tonight is really about a tour of the most spectacular, I think, things that we've done in science, but also to tell you that there's another story that's going on behind it. And it's an enormous human endeavour, and we hear a lot about people and manned space missions and so on, but there are thousands of people, space engineers and others, who are working very, very firmly on Earth. And I want to really tell their story today. So let's begin. These are some of the latest images that really give you a sense of what's happening on planet Earth. When we first started putting things up in space, there's thousands of various satellites and platforms that we've put up, we used to use false colour, but now actually we've got cameras in space. So much of what you see today in the spectacular imagery is life as it is. But I like the kind of blend. I like the fact that as a space researcher, I can choose to put colours in to enhance the image. But at the same time, now that you all have capacity with your telephones, for example, or your computers to have Google and to zoom right down, literally to your own house, to your car, to your person, you really want to have the right colours. Otherwise, we'll all be walking around in shades of purple and green and so on. And what I'm going to do is today, I'm going to unpack a lot of that. How did we actually build that capacity, both from the people and the engineering and the vision and the insight, and why did we choose to do certain things? So it's very glamorous in a way when you see these amazing photographs, and when you go on your phones and you can literally see details that we could never have imagined. So really, I want to unpack that and talk to you about some of the science, the instruments that we've designed, the people who've literally spent 20 years of their lives designing instruments that could never have been thought possible. And even as we were building them, we thought they would never be possible. So let's start with the Earth explorers. This is a little bit later in the history. Prior to this, we had a lot of work from NASA, from the National Aeronautics Space Agency from the US, building on their strengths from a moon mission and really feeling very confident about the kinds of engineering and what it took to put things up in space. But actually, Europe's been doing some very impressive things, and I want to tell that story from a European perspective tonight. So the Earth Explorers was an extraordinarily ambitious program of science. First and foremost, it was to equip scientists, both geologists and physicists and biologists and ecologists more in the later years, to really understand what is happening on planet Earth. And you'll realise as we go through this that it's actually really difficult to study many of the phenomena of planet Earth if you're stuck on planet Earth, because you simply don't have the scope, you don't have the breadth, you don't have the vision of what is happening all around the planet. And so these Earth Explorers, these were designed to tackle some of the most fundamental issues around our planet, but from the perspective of looking at planet Earth from away. So if we now move on to some of these, you can see the kind of period over which I'm talking. So these are rather of the last decade. 3 more still to come online: EarthCare, Biomass Flex, and we're still discussing the next ones that will come on in 2023. The one thing that you learn as you're going through the history of all of these different satellite missions is that we're getting better, we're getting faster, and we're getting more responsive and more agile in what we're putting in space. But there are thousands of satellites up, And so it gets more and more complicated when you want to put things in orbit that you don't actually hit other things, and they all have a lifetime. So you have to think about, well, am I just measuring something for the next 2 years to prove, or do I want an operational service? So what we're going to focus on first are the missions that go up to answer very, very good and deep scientific questions. And then at the second half, we're going to talk about the operational services. What do you need to know every day in a very accurate way and in real time? Those are the Sentinel missions. So we'll start out with a very exciting one. My sort of involvement is I'm passionate about this particular mission, and I had the privilege to actually go to the launch last year in French Guiana. It's called Aeolus. It's about atmospheric dynamics. It's probably the most sophisticated instrument we have ever built on planet Earth. And I say that because everybody else has said it, not because I said it. And, well, what is it? Well, when we talk about weather forecasts, most people are frankly unaware of how we get our forecasts. We have models and we have data. How do we collect those data? Let me just go forward a second. Balloons. We have many people setting off weather balloons all over the world, and as the balloon travels up through the atmosphere, it's taking readings, and those are giving us a kind of vertical slice. And then we have these super pressure balloons, this one particularly from NASA that was set off, and the idea was that it would be up in the high atmosphere and it would travel for about a year. And you can see on the little inset the kind of data trail that it had over that period. Well, it's not a lot of data, let me tell you that much. Right, so here's the problem. How do you then design something that will give us not models, not little points of data, but continuous mapping of the wind around the whole of planet Earth every day, every minute, wherever you are? Because that's really what the challenge is. To do good weather forecasting, you need to know what's coming. So the challenge 20 years ago was, could you design an instrument that would do precisely that? And give it in a timely and an accurate way? And what would be this instrument? And so what was designed was an instrument called Aladdin. And Aladdin is the first wind lidar in space. So what is it? Essentially, it's a laser. It's firing at 500 times a second, and it's actually detecting particles in the atmosphere in the 30 kilometers from the surface to the top of the atmosphere. It does this by emitting short pulses of ultraviolet light from a laser. It goes through the vertical profile, and then that bounces back. So if we look at it, it's essentially like a laser pulse. There's a small shift. As it goes through the atmosphere, there's different kinds of scattering from the molecules that are there of oxygen and nitrogen. And there's two kinds. There's the Rayleigh backscattering and the Meade backscattering. That's why you see the sky is blue. This is the instrument here. So it's quite a small instrument. And this difference, the Doppler shift between what goes out and what comes back, tells you two things. The time tells you the distance, where everything is in the atmosphere. But it even makes a correction because, of course, the winds are moving. So you need to calculate the speed of the wind because of where the particle was in the time that it's being measured. And that measure of change is what allows us to measure the velocity of wind. So you're measuring to within an accuracy of 2 meters a second through the whole of the atmosphere. So this is a phenomenal challenge if you think about it, people trying to measure this, capture the data, send it back to Earth, and then turn it into literally an almost real time and then into a forecast. So that's really what the challenge was. So here's the instrument. There were times in the 20-year development where I think industry gave up, then researchers gave up, then the space agency gave up, and then the researchers said, well, maybe we'll try again, and then the industry said, well, we can do it a different way, and so on and so forth. But the thing that caused the biggest delay was that it was the paint inside. The paint was too coarse because of what you needed in terms of the surfaces have to be so fine that literally the paint that was used was too coarse and had to be almost reinvented. And that's what took a lot of time. So every single part of the construction of this instrument required completely new technologies, new thinking, and so on. So I'm going to show you just getting up to the launch, there's a short film of what it took to really bring this to French Guiana for the launch, and then I'll tell you what happened afterwards. So this is about the diary of how you build an instrument and get it up into space. So if I could see the next film, please. So that's probably the most heart-stopping moment. The launch happens, stage one happens, and then you're in mission control and you wait. 12 minutes later, it's over the Caribbean. 15 minutes later, it's over Canada. 20 minutes later, it's over China. And each time a ground station is telling you, you know, we have it, we have it, we have it, we have it. And then it kind of descended down towards the Antarctic, and then there was silence. And we were sitting in the mission control and it wasn't coming online and nobody was calling us and everyone was thinking, oh, that's it, that's it. And then suddenly Antarctica wakes up, yep, we have it, we have it, we have it. So once you get the thing up, it has 2 complete orbits before the batteries and everything else run out, and it has to be running on solar. So you saw the solar wings go out and then it starts to fire up. It goes through a boot, just like your computer, and then you wait a bit longer, and then after about 3 or 4 orbits, everything begins and people can start to relax, and then you start doing all the instruments. What's truly amazing is that within a few days, this instrument was sending data back to Earth. Of course, we're testing it, and we're doing all of those things, but it's a genuine sense of achievement when you literally propel something in space. It was so sensitive. The reason it came on a ship was because we worried that if it went in an aeroplane, the pressure changes would be too much for that instrument. So that's how sensitive it is. And yet there you are, throwing it up, hurtling through space, and then you're putting it out there and hoping the thing's going to work. Well, it's a brilliant success. Then there follows, and this is the same for every single space mission, this thing called CalVal, calibration and validation. And you do all kinds of this before, but of course once it's up, this is reality. This is where you actually have to make sure the thing is working. So you have field campaigns all over the world. You even have people flying aircraft directly under the orbit, taking the same data and just seeing whether the satellite is getting the same data. So you have to check it and make sure that's all working. But already we can see, since last year, since it's launched, huge improvements in our ability to forecast, our ability to say to the world what is happening, especially in places where we don't have any observations, where we've never had observations, in the oceans, the polar areas, and also in the tropics. The idea, though, that you can have an instrument that is up there telling you in good time about events, about large-scale storms and hurricanes and so forth, it's truly remarkable. So the calibration and validation is still underway, but yet even now we're able to say it's working, and it's working extremely well. So for example, you can see on the left-hand side a picture over Western Europe, happened to be on the 10th of March, but it's literally able to discriminate between easterlies and westerlies, so throughout the whole of the 30 kilometers. We can talk about now wind speeds, so we can detect different spaces within the whole vertical, and we can, on any one day, for example, look at data that says, right, the jet stream has moved slightly and it's going to cause a problem for traffic, for construction. So that we can see is working. We can also see what is happening around cyclones. Now, the one thing Aeolus doesn't do, of course, is to penetrate the sort of depths and the thickness of where there's clouds, but it can tell you what's happening around them. So all the winds surrounding Idai, in this particular case, the cyclone that just went through on Madagascar, gave us a huge amount of knowledge about where things were happening around that island. And then you can combine that with other, and I'll tell you about them in a moment, about other satellites, Sentinel-3, that are carrying different kinds of satellites. So essentially, we move out of a research phase into an operational phase. And this is, in a way, the best that you can get out of a science mission. It becomes so powerful, the results are so, in a sense, this case, accurate, that people can then build and rely on it for all kinds of emergency services and so on. So hopefully in the future there won't ever be a situation of the great storm and Mr. Fish who won't be able to tell us what's going to happen. Let's move on to another one, another sort of spectacular satellite. So these are all the kind of like the hidden champions, the hidden giants of satellite science. And again, soil moisture and oceans. It sounds like a fairly esoteric thing to be studying, but actually it affects everything we do on Earth. So this particular mission put together a low-frequency passive L-band microwave, and it captures brightness of temperature. And once you have that, you can start to measure the moisture of soil, you can talk about ocean salinity, and it has proven to be a great success. So, for example, on the left-hand side, we were able to detect and really look at the spread of droughts. We can look at the spread of fire risk in Spain, for example. Here you can see on the bottom whether it's a high risk or a lower risk. We can also talk about the salinity, about acidification, ocean acidification. Now imagine if you wanted to go and measure ocean acidification with a ship. Well, you'd take a long time, probably 3 weeks, and you'd be able to do just a tiny part of the ocean by sampling and so on. But what the satellite is able to give you is literally a global view within a few weeks. So you can start to rely much more. And we have genuine problems putting out instruments into the oceans, but this, of course, tells you very quickly. It can tell you also about what's happening inside the storm centers, because what SMOS does, it talks about the frost and about the waves and about the storms. And similarly, here we can see in the bottom picture This is the thinning of ice, polar thinning, for shipping. Very, very important. So you can begin to detect where you can send ships through the Northern Passage, how they can cross through the Arctic seas. And again, this saves not only in terms of fuel and efficiency and economics, but also in terms of saving of lives. So SMOS is another great mission. And then you come to probably the greatest way in which satellites have changed our understanding of planet Earth, and that's on the 3D part of Earth. So it's impossible for us to think about the whole shape of the Earth, what's happening in the middle of it, and so on. We can only put a few probes down, and it's really difficult. But when we have satellites that are designed to look at not only the shape and the form and the sort of tectonic structures, then we begin to really see how planet Earth is working. So there are 3 missions here: GRACE, GOCE, and SWARM. SWARM is still up. GOCE came down, it's measuring gravity, and gravity brought it down, and the GRACE mission is hopefully going to be replaced by another GRACE mission. So what do? Well, let's start with GOCE. GOCE is Gravity Field and Steady State Ocean Circulation Explorer. It's essentially putting a gradiometer all over the Earth's geoid. And what that tells us is the shape. So where you have, for example, and this is what GRACE picks up, very large bodies of water, they actually distort the geoid. And so by being able to see where there are distortions, where there are domes, where there are valleys, where there are ridges, and you can see that the geoid is not flat. You can tell from the dark blue there's a bowl, where there's a dome, that's red, and where there's sort of flat, it's grey. So you can see that the geoid itself is highly, highly shaped. Then you can begin to look at not only the core, but also what's happening in the surface, in the mantle. So GOCE is a tremendous help in telling us the shape of the geoid. And then you can have, as I say, the GRACE measures, which tell us about water balances. So by changing the gravity and by changing the shape of the geoid, you can actually see where large bodies of water are below the surface. SWARM is really quite an extraordinary mission. It has, as it says here, the best geomagnetic field measurements and how it changes through time. And why do we care about that? Well, there are so many reasons we care about it, not least of which are your smartphones. So it's 3 identical satellites. They have magnetometers and they measure the electric field. And they fly together like a swarm. So essentially that's where the name has come from. And what they can do is, for example, they can pinpoint the position and movement of magnetic north. So magnetic north wanders all over the place, whipping from here over here, and has a huge impact on telecommunications. But the magnetosphere is our protective shield. And so having these missions which are measuring and telling us what's happening both outside and inside the planet Earth, we can really think much more clearly about how planet Earth is both evolving, but also how we need to respond to different things. So if you can imagine, the magnetic field is coming, it's like, as it says here, an ocean of superheated liquid inside, underneath our feet, and it's spinning around. So it's like a dynamo, and it's causing these electrical currents, and these are continuously changing. So the picture on the top is sort of an impression, an artist's impression, of what are called magnetic jerks. Every now and again, sort of the whole planet, it literally, the magnetosphere jerks outwards and does various things. We don't really understand why, but it has a big effect on what happens on the surface. And the plasma jets, they're kind of portrayed here, are things which we can observe in the magnetosphere, but we don't still really understand what they are. But we know that they have enormous impacts in terms of the solar weather, but also what happens on planet Earth in terms of telecommunications and so on. So what I'm giving you is a sense of we don't know, we don't understand, but at least now we're able to collect data in a sense that starts allowing us to test hypotheses, to ask questions, and to really explore what is happening on planet Earth in terms of its internal dynamics. This is more of a personal story, because what people are still frustrated by, and it's certainly something which many of the space scientists I work with are interested in, is can we forecast volcanoes or volcanic activity? And it turns out not yet. We're getting close to it, but not yet. And I put this up because I just happened to be actually there when St. Helens went up. I was sampling fish for my PhD. So there I was looking for this very elusive fish called the Salvelinus fontanalis, the brook trout. Very beautiful little fish, not like the brook trout, it's like big bullish fish. Anyway, there I was in the lake looking for this little fish because I'd heard that there was going to be potentially a volcanic eruption, and this was one of the few places at that time where the species existed. And I was doing some studies of the population, the genetics, and so on and so forth. Because this little fish is also an iconic fish when it comes to the molecular clock. So it's a very, very special species. And I was out there trying to find it and get it before the whole thing erupted, because I was pretty sure that afterwards this little fish wasn't going to be around. So there I was fishing. And it was quite extraordinary what happened, because despite all the sophistication of all the seismography and everything else, it went on the first tremors started in April, but it actually went through until late May before the eruption actually happened. And what happened on the ground was that, to begin with, it started to bulge on one side, and everyone thought, oh, that's where it's going to be. And then nothing really happened. There were a few vents. And then it started to move on the other side, and so on and so forth. And in the end, it actually erupted, as you can see, entirely on one side and wiped out not only the lake where I was, but all of the surrounding areas. Subsequently, you can see the Spirit Lake is sort of coming back, and things are sort of settling down. But what it really taught me was, despite the hundreds of people on the ground, and the same thing happening even today with many of our volcanic eruptions, we still haven't quite got a handle on where these are going to occur and where they're active. So this is an active area of where, as I say, space science is hoping to make an impact. And none more so then through these operational services. So as I said, you have the Earth explorers, scientific missions, trying to answer very, very specific questions. But actually, what I would say is the big, big job of satellites today is to provide operational services. And these operational services are highly, highly varied. So because of that, the European Union decided quite some time ago that they were going to put together a group of Sentinels, as they're now called, platforms that would really try to deliver on a daily basis knowledge and information and data that people could use and needed to know to go about their everyday business, but which would also create, in a sense, good enterprise. So could you create companies that would use these information? And it's very interesting because the model that was being, I guess, talked about at that time was one of a commercial model. And this is my only pitch for my own career, was that I felt very, very strongly that satellites and space was the place for the public good, and that we really, really needed to fight to make sure that all of the data that comes out of the space missions should be available to everybody. And so, fortunately, after quite some discussion and some interactions, it was decided by the European Commission that 3 billion euros would be invested from the public purse to put these satellites up there. And the European Space Agency was actually then given the job to do this. And the rest is history. What it is, though, is the most impressive, interactive, largest constellation of satellites which tell us pretty much everything that's going around on the surface. So it doesn't tell us about what's happening inside the Earth. It doesn't really tell us about what's happening around the Earth beyond the troposphere, but it tells us everything that we really need to know. Now, not all of them are up. There are many, many still planned, but I'm just going to take you through some of the key ones that we have. So the idea is that they should be accessible and available, that the data should be processed. You can process it for free, and there are big virtual machines that have been set up for everybody. And they are really, really transforming, I think, the way you go about living on planet Earth. So the Sentinels come at different times, but they always go up in pairs. There's always 2 versions. So you'll see for each one of them, they'll be launched at different times, but there's always 2. And that's the way you test accuracy, and you begin to turn them into operational services. So Sentinel-1 is all about radar imaging, and it's used more and more now for doing maritime traffic, for looking at things like here on the right-hand side, when the floods happened after Cyclone Idai, where does the water recede from, what's the impact, and so on. So really, really powerful. Can see through cloud. It's really one of our kind of stalwarts when it comes to looking at ocean services, but also land services. When you go to Sentinel-2, completely different. It's a multispectral, it's all about color, it's all about what you see, and you can already start building time series over the last 4 or 5 years. You can see the blend with what the Americans put up, the Landsat services. But these are now allowing us to see down to very high resolution. So essentially, if you go on Google Earth, you can see down to a house. But what these will do is it will tell you what's going on in the house. It'll start to tell you about infrared, about heat, and more importantly, what's happening in the land. So you can see individual trees inside forests, and then using Sentinels, you can talk about how much carbon they're storing. Are they healthy? You can see crops, and then you can see where the diseases are spreading. So for farmers, for forestries, specialists, for environment agencies, for all of the agencies and communities that are really needing to know what's going on in their environment, including deforestation and so forth. The Sentinels are genuinely the thing that they can rely on, that people can rely on, and they can turn this into something that you can, as I say, have on your phone. You can have it in your home. And to give you an idea, the pictures on the right are data that I've been working with my own Maasai tribe. They're using phones, they're going out, they're doing observations of individual points, and then we're putting them into the Sentinel data, and they're able to track the health of the forests where they're living. So these are not way out ideas. These are things which are actually being used today all over the world by people who really need to know what's happening in the places where they live. Sentinel-3 tells us a lot about oceans and gives us a forecasting setting. You'll see there's a testing that's going on between the two, A and B, and what's really good is that they're very, very close. They fly in tandem, very close together, so they're only, it sounds like a lot, 223 kilometers apart, but they're only 30 seconds apart, so it's a very sophisticated way. And what this is giving us is ocean forecasting. And then finally, and perhaps almost most significantly, we have Sentinel-5. Sentinel-5P, the precursor, is the one that can tell us about the air we breathe and the climate changes. And I really love it because when we first talked about this and designed it, everybody was very skeptical. No, you'll never be able to look at this stuff in the air, and the satellites won't be able to do it, and no, it's all very too difficult. But it turns out that we can not only talk about things like nitrogen dioxide, and I talked about that in my earlier lecture about some of the things that really do affect human health, but more importantly, the scale of it and the resolution actually means that we can now put out lists of the worst polluting companies, of the worst polluting installations. And then we can go back, and when they say, oh, you know, we fixed it, we can go back and say, no, you didn't. We can still see the plume. We can still see the pollution. So this has come as quite a shock. And Thomson Reuters have published a list of the top 100 most polluting companies and their installations. And it's very interesting that those data and the list have had a radical effect on some of those companies. So there's no doubt that at the same time as we were saying, you can use it as a citizen to check up what's happening. But if you combine it then with localized instruments, you can really begin to see that we have not only the way of monitoring, but also the way of implementing change and actually challenging people to make changes. So the Sentinels continue. We still have 6 and 7. We have 6 to go up, we have 4 to go up, and we have Sentinel-5, the not precursor. And these will all be going up in the next 2 or 3 years, spanning out next 4 years. And with that, then, we have essentially our planetary monitoring system. And then it's coupled to people on the ground doing all kinds of detailed measurements in situ. But essentially, we have a completely different view of planet Earth from all of these instruments. So the thousands and thousands of data that come in are free, they're open, and they're accessible. And so the biggest challenge is about training people how to use it. Getting, particularly in universities and colleges and schools, everyone to be, in a sense, comfortable with the idea of being a space scientist, or you don't have to be a space scientist. You can be someone who can just simply be the weather monitor or the water quality monitor or whatever. But there is no doubt that the gap between the space community and the user community, the everyday person who's just interested, is getting narrower and narrower and narrower. So if there was anything I would ask you in my lectures is to understand all the things I've talked about, the things that we've seen, the problems of plants, the plants and the crops and the pollution, all the things that we've discussed. Every single one of the things that I've been discussing, we can actually observe more comprehensively from space than we've ever been able to in the past. And so I'm going to put up a slide which perhaps is slightly provocative, because we hear a lot about people getting very excited about going on the Mars mission. This is the manned flight. This is people leaving planet Earth and going. So obviously there's a lot of excitement that followed the lunar launch and people going to the moon. And the Chinese are talking a lot about going up there and establishing a space station and so forth. But there's a very, very large community that's talking about going to Mars. So why would you want to go to Mars? Why would you want to leave Earth? Nice, safe place, everything's going in the right direction, you kind of know where you are and it's all fun. But it's not, is it? Let's face it. Planet Earth is not really. I'm not saying it's going to hell and back, but it's certainly not quite the place that it used to be. But there's actually a different challenge and there's a different threat. So not only are we doing things on planet Earth, but there are many things in space. And the more you read about what's happening in space, you realize that there are very large things out there. There are asteroids and there are many other things. And what we see on the horizon, certainly now that we have the possibility to look deep into space, is to understand that there are asteroids that are coming our way that are not only bigger, but certainly larger than the asteroid that hit and potentially was linked to the wiping out of the dinosaurs in the KT continuum. There's also very, very clear evidence that if they were to hit in any part of the planet, in the ocean, but certainly on land, the damage would be so significant that effectively the human race could be wiped out. So when you read the asteroid literature and you start to look at the numbers and you realize that with the data we have today coming in and being able to look in deep space, there's a kind of an inevitability that unless we can remove them and do something about them, sometime in the next few decades, there will be an asteroid that will hit Earth. What to do? Well, go to Mars, I guess, is the answer that some people think is a really great idea. And it's a very, very compelling argument when you hear what people think about, because what it does is it challenges our very existence, certainly as a social community. But it also asks questions such as, well, what would it take? You would be in a far lower gravity for a very long time. We have right now somebody who's up in the space station who will be there longer than before, so we're going to see already the negative effects of being in that kind of environment. What kind of food would you eat? How would you exist? And so by solving those problems, ironically, you solve some of the problems that we're going to have to face here on planet Earth. And that's why there's a lot of enthusiasm and a lot of investment in actually thinking about and planning what it would take to go to Mars. Now, there are people who really want to go to Mars. I'm not one of them, I have to tell you. I'd like to stay here on planet Earth. But they are genuine and they are really, really committed. And when we ask the question, how should we spend our money, there are some far-sighted people that realize that if you want humans to exist in the universe in the coming centuries and the coming decades, then actually you need to invest in protecting some people from the human race to make sure that we always potentially would have a presence in the universe. So that's the argument why the people want to go to Mars. As I said, I'm not one of them. And the reason I'm not one of them is because of what I think is really the case here on planet Earth. It's probably the most beautiful, wonderful place to live. It's the only place I know to live, but anyway. But we're doing a huge amount of damage. So thank you very much for being patient and coming. Those of you who've come to every one of the lectures, I appreciate it. Those of you online. And I would like to just end by giving you the chance to comment even on earlier lectures if you want to, but also on what you think about what you've heard tonight, and whether you want to be one of the people to go to space, go into Mars, or whether you'd like to stay on planet Earth, and what you might do to keep planet Earth in a really healthy way. Thank you again tonight. Thank you.